All right, welcome back to differential equations, and we are going to be talking about numerical methods tonight. Let me go ahead and push this off. Right. We had talked about Euler's method, right? And Euler's method, right, it looks like we have a curve. Let me get a better curve than that. Okay. A little bit more gentle. And what we did, right, is we had our beginning point, and we got an estimate for our slope, and then we took a step, and I know this is a huge step, but that's what we're doing. We got our next point here, right, and we said, okay, well, with this is our y naught plus our h times our slope. That's this little bit here. And then from here, we're going to reevaluate, and we're going to get a different slope, okay? And then so on, all right? And that was our Euler's method. Right? And we're going to just keep this piece going and do this and then keep going with it. Well, there was a gentleman by the name of Wayne. Okay, so this is going to be Wayne's method. We're not going to go into a huge numerical example here. We'll see why in a second. And Wayne said, well, this really undershoots or overshoots depending on what my original slope was. Maybe we can get a better estimate for a slope here. So what we're going to do is we're going to go ahead and evaluate the function at the step later, okay? And we're going to get, like I said, we're going to get that idea for a slope. So here's my slope for this one. Hopefully it's parallel to the other green one. Here's the red one or the orange one. And what we're going to do is we're going to take our first slope and our second slope, and we're going to average them together. So we've got our slope 1, right? This is our slope 1. And our slope 2. And we're going to average them together. And we're going to use that for our slope estimate now. Okay, so what we're going to do is we're going to have the same idea, right? Y new equals our y old, right? Plus our h times our slope estimate. And what I mean by our slope estimate is we're going to have this as h times, right? And what we're going to do is we're going to say m1 plus m2, all divided by 2, right? And that is going to be how we're going to arrive at our new point. Okay, that's Wayne's method. Now, it's important to get Wayne's method because we're going to be talking about Runge-Kutta methods. Okay, now, so there's two guys. Okay, sorry, it's the either early 20th century or late 19th century. So my apologies to the women that we did not treat you as people at that point. It certainly didn't allow you to do academics. So these two guys came up with an idea of saying, we average two slopes together, but we could average more together. Yeah, we could. I don't know if these two guys ever met each other, but they were both Germans. One was on the east side, one was on the west side of Germany. This is way before there was an East and West Germany. I don't know if they ever talked to each other, went to conferences with. I have no idea. Okay, but they both came up with this idea of, well, we have y new is equal to y old plus h times h slope estimate. Okay, now this is often abbreviated. If we have an RK2 method, that means they're using two slopes to get this estimate. And which two slopes are they going to use? Is they're pretty much saying that this is Wayne's method. Okay, we have RK4. We're going to use 4 slopes in order to generate an estimate for a slope. There's RK5, 5 slopes as an estimate. Okay, now we're not going to go through and do this by hand. Okay, there is a good reason for that, and that's because in MATLAB there is such a thing called ODE 45. Okay, ODE 45, and this averages the slopes you get from doing RK4 and RK5. And it's done that way because it's a really good way of kind of minimizing the error. Okay, you're good to about the 5th decimal place kind of a thing for your errors for this. Again, depending on what your H is, it's pretty much I think it's H to the power of 4. So if your H is small, it's H to the 4th power as far as your accuracy goes. But that's what we're going to be using for our differential equation solver, okay? And it's important that you know, like, what is it doing? Like, well, it's pulling together a whole bunch of slopes to do this. But really what it's doing is saying, well, let's have a y plus a step times a slope estimate, okay? Now, this slope estimate will be a little on the tedious side, okay? So this is why we use computers here. What we're going to do is we're going to say this is yn. Again, we're not going to do an in-depth numerical example here by hand. All we're going to do is kind of set up what's going on. You can look, and then we're going to have the computer go ahead and do this. Okay, so we have different weights, okay, of K1 plus a weight of K2 plus a weight of K3 and a weight of K4. Okay, I'm not going to derive the 5th one because it's just going to be plus 5 and, you know, W5 and K5. Okay, so what we're going to do here, I think the weights are like 1, 2, 2, 1, or I should say 1, 6, 2, 6, 2, 6, and 1, 6. So this all adds up to 6. So our weights don't skew our solution very much. We don't deal with this. But our K1, okay, this is just the slope that we get from Euler's method. This is just f of xn, yn. Okay, this is Euler's method here. Okay, our K2, okay, this is going to be f of xn plus alpha 1h, okay, and then we're going to have yn plus beta 1 h k1. So it's using the previous slope that we have in here in order to generate a new idea. So what's happening geometrically, right, is, right, here's our slope, here's our curve, and our first one here, right, that's Euler's. So here's our slope. Okay, notice what this is doing. This is saying h1 or xn plus some fraction of a step. Okay, I think that first one is 2, so it's half. Okay, so we're going some fraction of a step. Okay, and we're checking out what's going on here, and we're looking at, like, what's this slope. Okay, xn plus alpha h. Okay, and then we're going to do the same thing with the y's for that. Okay, just calculate for that, and then we're going to put this together and average these two slopes, right? So we're doing this guy to average them, and then we're going to, well, we're not averaging them yet. We're going to wait till we get all 4 of them. Okay, and something I want you to remember, that this is all to do one step. Okay, this is to do one step. So we're just going from our start x0 to, say, maybe this is our h, okay, to x1. Okay, it's just one step. So we might have several hundred of these to do. Okay, but our K3, okay, K3 is equal to f of xn plus alpha 2h, comma. Okay. These formulas are listed in your book. You are in no way ever going to be, like, forced to memorize these things. So don't worry about these formulas. No, you know, until you get to a class called Numerical Methods, nobody will ever ask you about this. Okay, hk1 plus beta 2 HK. I just want you to appreciate that you live in the 21st century. Okay, that's really all this is. Okay. And then K4, okay, is equal to f of xn plus alpha 3h, comma, xn plus, we had beta 2, this is beta 3. Okay, so now we're going to have beta 4, hk1, plus beta 5, hk2, plus beta 6, hk3. Okay, with any luck, someday you'll get to program this in a computer, to do a MATLAB class. You'll get to do this too. Okay. Like I said, though, MATLAB already has a command, ODE45, that does this for us. Okay, so you might have to program this in Python or something. Okay, but they, Runge and Kutta came up with like what the alphas and betas should be. In order to actually, we're solving this to make sure that everything kind of stays proper, but that's what we're doing with all of this. Okay, and that is to do one step of our differential equation solver. And like I said, you might have a lot of different steps. Now, we are not programming this. Okay, MATLAB has already programmed it. We are going to be using it. That's it. Okay, we are not programming this thing. So what we're going to do, right, you might have a problem, right, given, let's come up with a differential equation. We'll do a y prime is equal to, say, 2x minus 3y plus 5. Okay, something real tame. We could solve this by hand if we wanted to, right? It's a first order linear equation. You get an integration factor, just go for it. Okay. Might have some integration by parts going on here, right? Because y prime plus y 3y is equal to 2x plus 5. Our integration factor is going to be e to the integral of 3 dx, which is e to the 3x, multiply through. So once we get to this one, we're going to have integration by parts. This is just going to be easy, and then we'll go from there. Okay. So we could use Bernoulli, we could practice Bernoulli, but we're going to let MATLAB solve this one for us. Okay. So what we're going to do is we're going to define our, and there will be, right, I will put a document in our module so that you can have this. Okay, we're not doing a programming class. I just want to hand you, this is how you do it, and at most you're going to have to deal with like how to swap that around, and maybe your interval and your initial condition. Okay, so we're going to have an interval, and then we're going to have an initial condition. Okay, and I'll take us through this. Okay, I'll take us through the Octave, and I'll take us. I don't use MATLAB because I don't have it, but Octave works just fine, and I'll put a link in there for you as well. Okay, so what we're going to do is we're going to say f is equal to. We need an inline function. Okay, so we're going to say this is x, y. Okay, and then we're going to have 2x minus 3y plus 5. Okay. Later on, if we had, you know what? Let's do an x squared. Okay. Let's do an x squared here, because that'll force me to do something on this side when I'm writing it out. Okay. MATLAB only really works with vectors, and for those of you in linear algebra, you have realized how to multiply vectors together. And you can't multiply two vectors. Like you can't multiply like a 1/4 times a 1/4, right? You can't do that. But what we're going to do is we're going to multiply element by element. And the way we tell MATLAB to do that is we say dot caret for the square. None of that made any sense. That's fine. Just realize that when you want to multiply two x's together, you want to do that with x's, you need the dot caret. Dot caret or dot times. Okay, when you want to multiply two elements together. Scalars doesn't matter. Okay, so 2's, 3's, 5's, e's, pi's, all of that stuff doesn't matter. Okay, but if you want to multiply like an x and a y together, you need to do x dot multiplying. Hold on for a second. I'm going to go ahead and pause. So if you want to multiply x, y together, what we're going to do is x dot times y, and that'll do it element by element. You just have to do this in MATLAB because it expects a vector. Okay, you want to add them, x plus y, you just type in x plus y, it doesn't care. But multiplication is a little different, so you need the dot times, or if you raise to a power, you need a dot power. Okay, so we have 2x squared, okay, 2x dot caret squared minus 3y. Okay, we're going to need the times in here, and then plus 5. Okay, so there we go. And what we're going to do next is we're going to say we need we're going to use our ODE solver here. Okay, so we're going to say we need x, y. So this is going to plot x's and y's for us. Okay, and this is equal to ODE. Oh, let me do this. Okay, ODE 45. Okay, and then we're going to do parentheses, and we have to tell it which function would you like. Well, I'd like it to do f. Okay, where would you like us to solve the differential equation? So we need an interval. Okay, and this is the interval that x lives on. Okay, so you might want to say this is going to go from 0 to 3. Okay, 0 to 3. Square brackets, 0 to 3. And then it wants to know, like, well, where do we start? What's my, we have y of 0 equals what? So give it a number here. So maybe y of 0 equals 1, y of 0 equals a half. Okay, so let's go ahead, let's make it a half. Okay, y of 0 is equal to 0.5. 0.5. Parentheses. Hit this. This suppresses the output. If you don't do this, you'll get a long list of numbers. Okay, so this tells it, please don't show me the output. I'm not ready to see it yet. And then we're just good. What we're going to do next is we're going to plot it. We're just going to say plot x, y. We'll get a nice picture of it. We'll get a nice graph, and then we'll go on our way with having solved our differential equation. We have a list of x and y values for it, and we'll be all set. All right. So that's the pretty much the whole kit and caboodle as far as ODE solvers. This is as best as we've come. As we had a slope estimate, y plus a slope estimate, and then we just started refining that estimate. And about 100 years ago, this was the pinnacle of what we came up with. Okay, and this is what we still use. So let's go ahead and hit this one. Do I have an Octave up already? No, I don't. I'm going to go ahead and pause this for a second so I can put up Octave. All right, so let's see what we're going to do here. I'm just going to type in what I showed you already. Okay, so we're going to define a function. We're going to say f is equal to, and then we're going to have our at. Oops, there it is. Come on. There we go. At, and then give it our two variables, x, y. Okay, that means we have an inline function. Okay, and then we're going to go ahead and say which is the variable we want. Okay, so we have, what is this? We have 2 times x dot caret, right, for the 2x squared. Okay, plus, okay, and then we had, what did we do with this? We had, was it a minus or was it a plus? Just real quick. Minus y, minus 3y. Okay, so we're going to say minus 3y. Okay, we'll do it times, make sure that works out. Okay, forgive the ads, I'm sorry. We're there. And then plus 5. Okay, and then suppress our output. Okay, next is we're going to say x comma or xy, right, in the square brackets equals. Let's go ahead and wait for just a second here. Check something out. Okay, xy was equal to, okay, we're going to say ODE 45. Okay, there are other ODE formulas. Okay, there are other ODE things here. And we say, well, which would you like to give it? We need an F. Okay, we need a, what we're going to be on? We're going to be on 0, 3. Okay, and we had our initial condition of 0.5. Okay, so there we go. And then again, I want to suppress our output because I don't want all of this to come out. Okay. Actually, I'll show you what happens. Boom, and we get all of that. You don't really want to have that. Okay. So we're just going to hit this instead. See, no output. All right. Next thing we're going to do, plot. Okay, X, Y. And that way we can see everything that we're going to see. Oops, plots. Oh, I was not ploy, I went plot. Okay, plot. Plot X comma Y. Boom. And there is our solution here. Okay. And there's all sorts of things that you could do here. You could start typing in, like if I say help plot, it'll give me a bunch of little things to add in here. Okay. So you can change a whole bunch of different pieces with all of this. Okay. It's Father's Day. I'm seeing a lot of those ads. Okay. But yeah, and I encourage you, like, look through some of this stuff. You can do some of the little markers. You can make a little colors, all sorts of fun stuff. The two of them that we probably, or three of them we really care about is we might have an X label. Okay, and then we'll just say that's X, okay, or it might be time, or it might be temperature, it might be whatever independent variable you happen to have. Okay, see, and now it's set X, and then we might have a Y label, right, parentheses Y, okay, boom, there we are, the little Y there, and then we might have title, and put in a little, this was example for RK4. Okay, RK4, parentheses there. And then see, we have our little example for Runge-Kutta 4. We have our X, we have our Y, we have this beautiful picture here, and we are all set. Okay, so I'm not making, we're not programming. Okay, I will definitely be adding a little MATLAB file for you to go through and do this. All you're going to have to do is change the function, right? So you're going to change the arguments that we gave it. Okay, you're going to have to change some of these things. Okay, but that's it. Okay, everything else you should be able to just, cut and paste and deal with it that way. All right, because I don't want us to have to worry about all of this. Okay, but if you're going to be using MATLAB in the future, get a little bit of a, a feel for it. Being able to graph well in MATLAB, it's not the easiest thing. It is definitely a learning curve to it. So, definitely try to play around with a little bit. Let's do the same plots, except let's go with the blue line. Okay, let's do blue. So we're going to say plot X, Y, blue. Oh, never mind, that was the same one they gave us as a default. Let's go with green. See, that changes it. Okay. Or what if we want green O's? Think that'll do it for us? Look at that. Okay, so I do urge you to kind of, I need to change my title, axes and all that other stuff in there, but I do encourage you to go play around with this a little bit, okay, and deal with, oh, it didn't like T. I want stars. I'll do stars. Okay, so green stars, yellow horseshoes, etc. Okay, so play with that a little bit, but that's what we're doing for this section. Okay, so nice, easy stuff. It takes a bit to get used to, though. Okay, so thank you very much for that, and I will go ahead and end this and post some things for you guys. All right, thank you.